network tries to mimic the behavior of the functioning of the brain. So basically, we are looking at inputs, input data, input 1, input 2, input 3, that are fed into the neuron, and there is a certain output. Supervised learning, we have access to inputs as well as the outputs, and the objective is to learn the neuron to learn how the neuron functions. So when we are talking about inputs, we are talking about the input data like x1, x2, x3, which are independent variables. They are independent variables, and they are related to neuron in some manner. And each of these input data, they have a certain weight associated with themselves. It's the weight. It's the weight of the input data with respect to neuron. So weight is like, it's something like importance. It signifies the importance of this particular input data with respect to the output given. Okay, there is another input data x2. Weight relayed signifies its importance with respect to its output. Okay, so we will talk about these things immediately now. Right, but few things at the very outset. The input data, there can be a vector of input data, a vector of input data. They can be dependent on each other, but usually they are not dependent, and these are known as features. So x1, x2, x3 to xm, they are known as features, which may or may not be dependent on each other. Nowadays, it's possible to process both kinds of features, but usually they are independent. Well, that depends. And the output data, that can be that could be continuous value, or that could be a discrete value. That it need not be numerical only. It can be categorical variable also. Right. So to represent the neuron, we can be representing the inputs in green, x1, x2, x3, till xm, and the outputs can be y1, y2, y3, and so on and so forth. So it's a basic representation, just to give a higher level representation. I will be using this kind of diagrams, right? Now, so what we are looking at basically is right. So what we are now looking at is input data, neuron, and output bank of output values. Let's talk about the basic perceptron that was initially proposed during 1960s, I guess. So the basic perceptron looks like this. We have input data. I'm going to go a little fast here because these are very basics, and I guess many of you are already aware of it. No problem. If you have some questions, let me know. Okay. So bank of input data, x1, x2, x3, xm. Each of the input data has a certain weight associated with it. And what we first do is we take sum of all the input data. Well, that's pretty intuitive because we are trying to process input data at one time. So we take a sum of it. So the input signals, it forms a weighted sum, right? Now the idea is to pass it through a threshold function. The threshold function is like, okay, the threshold function is based upon your requirements, the context. It can be, let's say, a price of an apartment. It can be anything. If it matches if it is above the threshold, it passes through. It fires, which is basically that if the activation level exceeds the threshold, the neuron fires. And what do I mean by neuron firing? Is that it passes through the threshold function and there is a certain output. Now, of course, the output value should be equal to the real output. The output of the network should match the real output, and that's the whole objective. So, yeah, so that's your basic perceptron. This is a very simplistic representation of the functioning of neural networks. Each of the weights, they signify the synaptic behavior in the neural cells, and the threshold function, in a very simplistic manner, represents the firing mechanism in our neural cells. However, this is a very simplistic representation because there is just one function, the threshold function, which influences the learning. In reality, we know that we learn in a very complicated manner. So a simplistic function such as a threshold function is very limited. So what to do? How do we construct this kind of function? Let's say a linear function. So it's pretty easy. Let's take in all the inputs, all the weighted sum of inputs. That's the first step. Let's take all the inputs, weight them by a corresponding weight, and there is a bias. And the second step is to second step is to apply a non-linearity. So why non-linearity? Because these are functions, they are not very useful. So we can ask ourselves, why are linear functions not so useful? Well, if we only apply a linear function here, it means that all layers of the neural network, I mean, it doesn't matter how many layers we construct, at the end, all we will have will be one linear function. All the layers, they would collapse into one. And so it doesn't matter how many layers or how complicated the network, the complexity of the neural network will not determine, will not have an influence over the efficiency of output, because eventually all the layers, they would collapse into one linear function. And so if the data is non-linear, is complicated enough, function will not usually be efficient. Now, I don't want to go into much details, but you can ask why we don't prefer linear functions. Simply because most of the data that we are trying to deal with, they are distributed in a pretty skewed fashion, in a pretty non-linear way. And using linear functions, all we can do is we are able to form only linear discriminate functions. That is the classes which can be divided by a linear line or hyperplane. And most of the functions are complex. That is, most of the functions we are looking for, functions here we are looking for, we are trying to deal with nonlinear. We are trying to deal with nonlinear dynamics. We are trying to deal with data which is highly skewed and mostly non-additive. And linear functions or hyperplanes, they are just not sufficient enough, just not efficient enough to classify such such input distributions. So we have to inject the nonlinearity here. And so what we do is the second step, we inject the nonlinearity. So you would see the difference between first step. First step is simply summation of all inputs with their corresponding weights and bias. Just as we discussed before, bias is the offset. There is a question from Dr. Venkatrama.
Hello, sir.
I cannot really access the comments here. There are many comments coming, but I cannot really see them. I don't know why. Please go ahead with the question. Yeah.
Hello, sir. In the equation, what is the use of plus B?
Yeah. So that's the bias, my friend.
Okay.
That's bias. So bias is basically an offset. I was asked the same question. So let me put it into. Let me talk about it a little more. Many of you are you want to know what is B. B is the bias. Now, what is bias? Bias is simply the offset. When your function, let's say this, all the inputs are 0. So when all the inputs are 0, what's the value of output? Well, that's your bias. Okay. That's like initial conditions. Is that okay?
Okay, sir.
Great.
Okay.
So your bias can be 0 as well. That's not a problem, but that's a special case. Usually, you can put B equals non-zero, and during learning, if your offset is really 0, B will converge to 0. Okay, so that's how it happens. So that's how it. That's how we treat. That's why. That's how we are staying general, right? Okay, so let's go to the second step. We have the nonlinear function. So now we have injected the nonlinearity into our function. Phi is any nonlinear function, and this phi is known as the activation function. So phi of x is the activation function, which basically determines the output. Right. And the third step is, well, to simply put the output itself. So let's put the output, and you get the output, which is y in red. So we have the inputs. All of the inputs, they have their corresponding weights. They pass through the summation function. Then they pass through the nonlinearity, and eventually they give a corresponding output. Yes, is there a question? Right. Now, so let's go ahead. Let's try to look, what do we have inside this? So inside this neuron, we have two basic functions. First is summation, and second is nonlinearity. As we discussed, this is known as the activation function, and here the activation function is sigmoid. Well, what's a sigmoid function? We'll discuss all in details later on. For now, it is important to understand that we have two basic functions, the summation and nonlinearity. That's it, followed by the output. Let's go. This is known as an activation function. There are different activation functions in use. There are several functions. They have some typical properties. Let me present you some of the activation functions, but we are going to discuss them in details later on. So the function that you saw was a threshold function, simple threshold function. It's a binary step function. Well, if your x, that is input, remember x is here. If your vector x, your input, which comes here, let's say your summation input, okay, take the summation and feed that summation in. So now I'm going to talk about the input of the activation function. If that input is less than 0, then the output is 0. And if the input is more than 0, then your output is 1. So it's like, you can classify your data into 2 classes depending on where the data belongs. Let's say the data belongs, let's say you put -6. So here, let's say you have x1, x2, x3, xm, you make the summation. When you make the summation, you get -6. So -6 comes here. When -6 comes here, well, you use this activation function, and -6 is less than 0, so your output is 0. However, scenario 2, if you take the x1, x2, x3, or you take the summation, here, once you get your summation, you find it's, let's say, number 2. Its value is 2, which is more than 0. So once you feed that in, well, same. And if you are using this threshold function, then the output value is 1. Why? Because your input is 2, which is more than 0. So you can see that if you train your network like this, you will be able to classify 2 types of data. Type 1 is class 1 is that which is less than 0. And class 2, the second class, the other class would be the data that is more than 0. So threshold function can be used for 2-class classification, but here we can see that there is a very abrupt classification. We ask ourselves, can we use a similar strategy to do multi-class classifications or do classification in a more sophisticated fashion? So let's look at this activation function. Now, if you keep everything same, just replace this part. Don't use the threshold function, but let's say you use the sigmoid function. Look at the sigmoid function. It is also like threshold function. It is between 0 and 1, but there is a smooth increase in its slope is smooth. It's a smooth spline. So the slope is smooth. And how it helps us? Well, it helps us because it can classify data depending on where the data is. So let's say the data is here, very near to 0, but on the negative side. So it would classify it in this class, which belongs to, let's say, belongs to 0 and 0.2. However, if your input is, let's say, far from 0, but on the positive side, let's say it's 6, so it would classify it somewhere between 0.8 and 1. So you can be using this function, we can be using to classify different kinds of data. And that's a great thing, because now we don't need to put constraints on we can deal with many kinds of data here. We can deal with different kinds of data, and this sigmoid function helps us to classify different kinds of data with different properties. Is that okay for everyone? Do we have questions here? Okay, so let's go ahead.
Just as a goal, do you ever see to order Jenkins? So we're creating an API that will allow a customer or an agent to order a token, order a hot token, or
I could not understand. I could not understand the question at all. That was not clear at all. So I have some comments. Yeah, okay, it was some disturbance. Okay. So let's go ahead. So sigmoid function we talked about. Now let's look at the hyperbolic tangent function. You will appreciate the fact that in fact this function is something very similar to sigmoid function, but let's look at its range. It can classify, it can, its range is pretty large, larger than the sigmoid function. Sigmoid function is between 0 and 1, while this hyperbolic tangent function is between -1 and 1. So it can be used to create almost double number, almost 2 times the number of classes. So basically, the range is larger. The range larger means, well, you have large possibilities for classifications. However, please look that the slope here is greater than that of sigmoid. So while sigmoid, it decreases slowly, the tan h, the hyperbolic tangent function, it decreases pretty fast, which means that if you are going to have a lot of data around 0, which are, let's say, which are dense in some sense, a lot of data around 0, then they are going to be they are going to be not classified properly. They are going to be put in the same group. Let's say let's say we have a data minus 0.1 and 0.1. So minus 0.1 and 0.1, they would be classified almost very near to 0. And because you see the slope is pretty high, is pretty steep than the slope here. So here you have a big expanse. Here you can have those two data classified within the groups, within the classes that are well separated, or they have a large distance between them. But here they would be classified into classes that do not have enough distance, or do not have as much distance as the other. Do we have a question here? Okay, if we do not have a question, let's go ahead. So the fourth one is ReLU function, which has been activation function, which has recently come up and has become very efficient in the deep learning community. And we will talk about it more at the end in much details. Let me just tell you that ReLU is pretty different from that of sigmoid or tan h. Here you see any data which is 0, which is positive, which is more than 0, would be, well, it would the output would be the data's value itself, and any data which is less than 0, it would simply, the output of the neural network will simply be 0. So in a way, it separates the data more than 0 and less than 0 in a pretty remarkable fashion. But how does the learning affect all that? How does this activation function affect the learning itself? Well, we are going to discuss it in pretty much details later on. So let's go ahead. So these are the 4 most commonly used activation functions. And there's also softmax function, which we are going to use later on, which we are going to talk about later on. Okay, so as we said, so let's go ahead. As we said, we said that linear functions, they are not so useful in classification for the classification purpose, because essentially, if we are using just linear functions in all the nodes of the neural network, then what we will be eventually able to do is to create linear discriminant functions. That is, we will only have linear discriminate functions. That is, the classes which can be divided by a line or a hyperplane. But in face of skew data, in face of nonlinear dynamics, in face of data distributions, which are highly skewed or distributed in a complicated fashion, or which are not convex, let's say, linear functions are not going to help us a lot. Okay, but that's the motivation of using nonlinear activation functions in the nodes. Now we talked about the inputs. So let's say these are input nodes. We talked about the neurons. So that's your input layer. This is your the first hidden layer, right? That's your output nodes here, and all the nodes, all the inputs, they are connected to all the nodes, and all the nodes, they are then connected to the nodes of the layer ahead, and that's how you construct the basic, most simplistic feed-forward neural networks. So this network that we see here is the multi-layer multi-layer feed-forward neural networks. So this is actually, in principle, a deep neural network because it has more than one layer. So, from the point of view of nomenclature, this is a deep neural network. But of course, what we are going to talk about later on is going to be very different from this. Okay. So that's your multi-layered feed-forward networks that you can use to approximate the unknown functions and unknown dynamics in principle. It has the universality property, which means that it can approximate any given function if sufficient number of nodes and sufficient number of layers are used. Right, let's go ahead. So, well, to give you another picture, this is a picture I've taken from internet, and just for the representation purpose, I failed to give the reference here because I forgot to write the reference. Well, it's a picture from internet. Just for a representation purpose. So we have the inputs here. All the inputs are connected to all the nodes of the first layer. Well, there is a summation of the inputs followed by non-linearity. All the nodes of the first layer, they are connected to all the nodes of second layer. Similarly, all the nodes of the second layer, they are connected to all the nodes of the third layer. And then finally, we have one particular output. Okay. In all these layers, in all the nodes of the neurons, we have summation followed by non-linearity. Okay. And of course, these non-linearity activation functions, they can be different. They can differ from each other depending on their purpose and depending on the architecture. But that's your general architecture right there. And the output is one. It's just one simple output, but it need not be so. So we can have several layers with several nodes, and output layer can have several outputs. So it need not be just one output. It can have several class classification, a multi-class classification, what we call it as. So the outputs can be multiple targets, and we are going to talk about softmax activation later on, which helps us to deal with such cases. Okay, till now, do we have some questions, please? Perfect. Okay, so let's go ahead. So let's talk about the neural network. Let's see how it functions. We have the input layers, input data. Each input data is connected to each of the nodes of the first layer, and these black arrows that you see, they signify the weights. Okay, so input nodes, first hidden layer, hidden nodes, and the output. Now, in each node, we have summation followed by the activation function. So this activation function can be sigmoid, tanh, or ReLU function, followed by the output node, where again we have summation followed by the sigmoid, followed by activation function. Okay, so that's your very basic neural network. So let's now talk about how the neural network functions. And to explain that, uh, let me take a simple example. So let's say you are searching for an apartment. Of course, you are searching for an apartment based on several factors. You are going to choose the apartment. Those factors can be, for example, the size of the apartment, the distance from station if you are going to work and take a train very often. It can also be the age of the building, and there are many factors, but we are going to only consider these three. Bear in mind that the units of all these inputs, they are different. So the size is in meter square, the distance is in kilometers, the building is in years. So these are different they belong to different categories, and each of these inputs, they are related to, they give a certain output, and they are somehow related to the output. So that would be defined by the weights associated to these inputs. And the price can be linearly related. For example, it could be the simplistic case, it could be linearly related. It need not be linearly related, but it can be linearly related also. So that's this image gives the simplistic idea that the output is dependent on each of the inputs, okay? And each of the inputs, in fact, output is dependent on the weighted sum of each of the inputs. So we have summation, we have each input weighted by its importance, weight 1. X2 is weighted by its importance, weight 2. X3 is weighted by its importance, weight 3. And there is a certain bias. Bias is when you put x1, x2, x3 equal to 0, bias is the value of output. Okay. Now, so let's go ahead and let's see how it functions. Well, basically, these three inputs, they are connected to all the nodes. And let's say for a certain price, you have a certain price here, output, which is determined by, let's say, a combination of size and building age. So size may be large of the apartment, which is good, but the building age is also large, and that is not good. So let's say the first node is capturing that property. So if that is the case, then what is going to happen is that the weights here on this arrow and on this arrow, they are going to increase, or they are going to be strengthened, they are going to be reinforced, and the weights on the other arrows, they are not going to be as high as the weights on these two arrows. If that's the case, that may not be the case, but if that's the case, that is what is going to happen. So basically, if weights on these two arrows, first arrow here and second arrow here, if weights on only these two arrows, full arrows, are let's say very high, and the rest of the weights are low, it means that a combination of size and building is having a significant impact on the output, which is the price. Okay, but that may not be the case. So we have to give all the possibilities. So in fact, all these nodes are connected to all the nodes, and these 4 different nodes are actually in some way capturing some of these properties. They are capturing, oh, how is the first is related to second, or second related to third? How are all these three related to each other? And they are capturing different properties. Since we will be using nonlinear functions, we cannot really know. Well, nowadays we can actually visualize. We can visualize, especially in PyTorch. It's easy to visualize which weights have learned what features. That's how we use transfer learning. But let's assume that we don't know all that. Let's say we are still in 2000s or 1990s, and we are talking about the basic functioning. So if that's the case, then we are saying that, okay, we have a nonlinear function which is capturing some property of the distribution of the input. So what we are saying is that each neuron has weighted inputs from other neurons. That's right, you can see it. Each neuron has a weighted input. The input signals, they form a weighted sum. If the activation finally exceeds a threshold, then the neuron, it fires. You see, the first neuron will fire, second will fire, third will fire, fourth will fire, depending on what property is being captured and depending on how the output is related to that captured property. Okay. Right. Do we have some questions here?
Sir, is each node related to each other in some way?
Each node are related to in this simplistic architecture, no. But in recurrent neural networks, for example, we can be connecting two or several nodes in various ways, and then we can be capturing their effects on each other. There's also another question: can we adjust the weights optimally using any global optimization techniques? That's right. We can actually. Well, that's what we are going to do. We are going to adjust the weights optimally. The whole training procedure, the whole training process is just that. We are trying to find the optimal weights for all the nodes using different kinds of optimization techniques, such as gradient descent based methods. We are going to talk. There's another question: how we have identified the factors for node. How do we identify the factors for? Well, that's a I guess, yeah. I guess what you're trying to say is that what kind of functions we have for nodes, each nodes. That's a pretty interesting question. A priori you cannot. A priori you cannot. There's no hard and fast rule to know in advance what kind of activation functions to use. But I'm going to present different kinds of activation function, and well, if you know the properties of activation functions, you know which ones to use and which ones to not, and then you can be testing. So let's say here we have, let's say here we have the price is not just one category, but let's say there's a different classes of price. So in that case, I will not use a sigmoid function here, right? I'll be using, let's say, well, I can actually also use sigmoid, but that the performance is not good. I might want to use softmax function because that gives me a better results, because softmax function can deal with classes pretty efficiently. So we will talk about that later. Of course, that comes from experience and several case studies. So when you do different case studies, when you process different sorts of data, in robotics, it's a different approach. In vision, it's a different computer vision, it's a different approach. And yeah, that so on and so forth. It comes from practice, but yeah, that's the general idea. So I hope I answered that question, and I think we can all go back to these questions later on when we are finished with the course. You can be asking me the same question later on, and perhaps we will have a different answer. you will have a different vision altogether, because we are in some way going to address these points during the course. How do we identify the factors for nodes? Okay, threshold for neuron. Well, threshold for neuron. Well, we are not using a threshold function here, so I don't know about that. How to select number of nodes in hidden layer? Well, that's a hyperparameter. That's like that you don't know in advance. You might like to start with. It depends on the complexity of data. You might like to start with 20 nodes, for example, and then you will find that it's in fact 2000 nodes which are working well in your context, or maybe not. They are leading to overfitting. So we are going to talk about what is overfitting, what is underfitting, how to tune these hyperparameters later on. They'll give you more details. You mentioned the transfer learning, please give more detail. We will talk about it later on, but transfer learning is nowadays, you can visualize it as, let's say, having several nodes here, and let's say a face is being detected. So this particular node, or let's say it's not just one node usually, but let's say a set of nodes is capturing how your nose looks like. And well, if you can visualize that, if you can see that, oh, it's indeed nodes which are capturing the property of these nodes, which are capturing the property of your nose or your mouth, then you can be using these weights. You can be taking out these weights and using it in another architecture to have similar results. So that's pretty much transfer learning, but we'll talk about that later on. I don't think we are going to talk about it. There's plenty of material, but we can have a discussion. Okay, so let's go ahead. Continuing the similar example, we have three parameters. Let's say size, distance, building age, and let's say distance, they are having certain influence, but they are independent to each other, so they can be related in this way. They are not dependent, and then you will see that depending on the price, this property will be learned. So yeah, so that's the thing. So what's going to happen? We are going to have several training. We are going to have several input data. Input data 1 with x1, x2, x till xm. Input data 2 with xm, x1, x2, xm. Okay, each input data has m elements, and each of input data has a corresponding output. So input 1, x1, x2, xm, has an output price. Input data 2, x1, x2, xm again, has an output price, right? So this training is going to happen several times, and after several training, it leads to optimal sets of weights. That the idea is to learn what are the weights of these nodes, because remember, it is the weight which determines the importance, which determines how each input data is related with each other. So it's the weights. So basically, we are going to find the optimal weights, the most suitable weights that give us that give us the accurate output. So that's what we are doing. After several training, we are going to have the weights that determine the nonlinear relationship between inputs and targets. Targets are the outputs. So the question is now, how do weights adapt? Or in fact, by asking this question, how do weights adapt? We are asking the question, how do neural networks learn? Okay, is that okay for everyone? Do we have a question here? To pose the question, please write it down in the chat box. Now I'm able to see the chat box, so I'll be taking questions as I'm getting free during the presentation. Okay, so let's go ahead. So let's talk about the learning in neural networks. How do neural networks learn? So to show you how neural networks learn, I have taken the same example. The same example we talked about, and right, I'm having a little problem here. That's fine. So we have several inputs. we have the summation of inputs, weighted sum, we have the nonlinearity, and we have the output y hat. This y hat, in French it is known as y chapeau, is basically the output from the network. But your real output is y, and it can be different. And those of you who are from estimation theory, from estimation background, you might know that we have the real observations and we have the estimated observations. And the idea is to estimate the parameters based on real observations. So in this case, the red one, y, is the real observation. And the blue one, y hat, is the estimated output by the neural network. Okay? And of course, they both are not same. They are different. Y hat is different from y. There is a difference between these two. And the whole objective is to change the parameters, change the weights in such a way that your y hat is equal to y for any input, for all the inputs. Okay? So, of course, there is a difference. So what we do is that we calculate the difference between the estimated output and the real output. This is calculated using a loss function, which is the error between, you see a difference here between y and y hat, and that's the error. Okay, and the question can be, oh, why do we use half here? Why do we have y minus y? Why do we y minus y hat square? Well, those of you who have worked in optimization, those of you who have worked with gradients, you will know that what we are going to do is take a gradient of the loss. The gradient of, let's say, this term, y minus y hat, you will 2 times y minus y hat, followed by derivative of this term by y. So this power will cancel the denominator, because if you derive, let's say you take of this loss with respect to y hat, what you get is multiplied by 2 times y minus y hat, followed by further derivatives. So the square cancels the half. That's why we use half here, just to not have some scaling issues. And why do we square really? Well, we square because it's the same reason why we use least squares and not least cubes. That's because quadratic functions are easy to handle. And you also have only positive values for any non-positive value of y hat or y. You're always going to have positive values, and it's pretty easy easy to handle quadratic functions. So that's why we use this is your function. Sorry, is there a question? Okay, I guess that was a noise. So we have the loss. The loss is fed backwards. So this is known as back propagation. We will talk about it in a little. So loss is calculated, and loss is sent back to the network. Please mute your microphone, please. Request to all the participants, please mute your microphone, and especially when you join the course, it's pretty disturbing. Thank you. So, right now, once we calculate the error, it is transferred back. It is propagated back into the network, which is what is known as back propagation. So what you're seeing in yellow is back propagation of the loss. So what we have done is we have blue information propagating forwards. We take the output of the network, we match it with the real output. If the error is not zero, it means there is some loss. If there is some loss, then it is fed back into the network. Now, it is fed back into the network, and the idea is to change the weight of the network in such a way that this loss in yellow, is minimized. Okay? So eventually, in the most ideal scenario, your weights will be optimal. They will be perfect. Perfect based on your context. And when we say perfect, it means the output from the network will be exactly the same as the real output. Well, that's never the case, but that's the idea. So let's go ahead. That was input 1. Remember, we did it with input 1. So let's do the same with input 2. We do it with input 2. So remember, input 2 has all this data. Input 2 has x1, x2, x3 till xm. All this vector of data is propagated forward in the blue line, and there is a certain y hat in blue. The real data, y, is red, and there is a difference between the blue and red, and the difference is calculated using loss, and the loss is propagated backwards for input 2 also. Similarly, for input 3, we have that. Input 4, we have that. Input 5, similarly, there is some error and it will put back. And let's say input 6. So we have 6 input data. So we have done this 6 times now. So give you an idea, what we have done is we have, for 6 input vectors, we have done forward propagation in blue and backward propagation in yellow. So you see the 6 estimates by 6 input data and their estimates by the neural network, and compared with the real estimates, there is always a difference, except the 6th one where the input is, the y hat is similar to y. Well, that's the ideal case, right? Well, so what's happening is that when you do this kind of tuning, you will expect that slowly the difference between the y hat and y vanishes and it becomes the same. Well, there are different ways to do it. So we are going to look at the first way of learning, which is known as batch update. That is one iteration of batch update, which means that you consider the input data, feed the information, calculate the loss with respect to its actual loss. And the idea is to backpropagate the loss which is obtained with respect to all the 6 inputs at one time. So in fact, your loss, which is being backpropagated here, loss is the summation of first loss, second loss, third loss, fourth loss, fifth loss, and sixth loss. Take all the losses, get a sum, and backpropagate this loss in yellow into the network. Okay? And if you do that, then this is known as, what you're doing is you're updating using a batch of data. So you're updating your weights, you're updating the weights of the network using a batch of data. That batch, what is that batch of data? That batch of data has 6 elements. Input 1, 2, 3, 4, 5, 6, right? So let's say you have 6,000 data. So you're going to feed in 6,000 data one time. You feed it several times, it doesn't matter. Take all the losses, make summation, and you backpropagate only one time using the whole batch data. And that is known as batch update. So when I show you this figure, it means that you are doing the update using all the 6 losses at one time. So you're updating all the weights of the network, using the total loss. Is that clear for everyone? Do we have questions here?
Hello.
Yeah, hello? Fine, let's go ahead. Fine. That's your weight. That's your batch update. Um, yeah. Okay. Now that's the batch update. The idea is the objective is to minimize this loss, this total loss, using which the loss which is which is calculated using using the individual losses, and all the weights are updated. Now, you will also come across the term one epoch. So one epoch is basically when the training is done on the entire data set. So here, let's say you have six data sets, input data sets. So when you train using all of them at once, when you have finished training all of them, that would be known as one epoch. So in batch training, if you have just one batch which has all the input data, that would be one epoch. Okay. And you would take the total of all the losses, and you will back propagate the loss into the network and update all the weights all at once. Okay, let's go ahead. So now we ask our questions. Now we ask ourselves a question: how to minimize the loss and update the weights? Well, we said we are going to minimize the loss. We are going to update the weights. We looked at how it can be done, but we don't really know how back propagation can be done. We saw, but we don't know how to minimize the loss and update the weights. That's what now we are going to look at, and that's basically how is your neural network learning. Well, let's see how the neural network learns. So neural network learns. Well, it can learn using many algorithms, optimization techniques, but one of the most very usual way of learning is gradient descent, and pretty efficient, and also pretty very, very famous, and almost always used, at least for the first time. If it really doesn't work, then only, well, we go for other ways of learning. So gradient descent is really one of the major optimization, iterative optimization methods. So gradient descent is basically an iterative method for finding the minimum of any given function. One question is, why do we have an iterative method? Because remember, in neural networks, you are not dealing with linear functions, you are dealing with nonlinear functions. And most often, as it is, the solutions, they do not have a closed form. Solutions are not available at all. And the objective is to minimize the loss function, that is the cost function, or to have the minimum mean error between the neural networks and the actual values. So there was a question in batch update, we consider all set or subset. Well, if you talk about a batch update, since we are building from the initial concepts, I'm not talking about mini batch concept. I'm talking about the batch update. And there, I'm just talking about, we are talking about taking all the data, okay, at once before the back propagation. We are going to learn about mini batch soon, which you might be referring to right now. Okay. So this question was from Subhash Kumar. Okay. So let's go ahead. Right. So I'm going to talk about the gradient descent based method. The question is, what is gradient descent? I'm going to use the very usual and famous analogy given by many teachers and researchers around the world, which is the analogy between the process of climbing down the hill to find its bottom, which is very similar to what we do in gradient descent based optimization. So remember, we chose our loss function as a quadratic function. So you will see that in red, that's your quadratic function right there. Well, it can be a line, but usually you have, when you have multi dimensions, you don't have a line, you have a hyperplane basically. So it's a sphere. In fact, it's a hypersphere, and we are just looking at we are just projecting it on a 2D plane, right? So so let's say your initial weight, the weights of neural network is here. You are here initially, and what we are going to do at the next step is we are going to see. We must remember that our objective is to find the minimum of the function, right? Minimum of this hill, the red hill. So what we are going to do is to, at each point of time, we will try to come down. So at next, let's say I am here at black spot and I want to come down at the red spot here. I'm trying to see if I can have my laser some way or the other. Can you see my laser? Is that okay for everyone? Vijay, can you see my laser?
Yes, sir.
Okay, perfect. So okay, right. So I am here, and at the next instant, I want to. What I'm going to do is I will see the direction which leads me to a minimum value. So what is the direction? Remember, direction is given by slope, and slope is given by derivative. So I'm going to find the derivative of this function, this red hill, with respect to given direction, which is, let's say, x or y. And I'm going to take a step forward in that direction. So what I will do is, at this point, I will take the partial derivative. Why partial derivative? Because the function can be, a function of sensitive to many variables. So by taking partial derivative, I'll take the slope, with respect to a given variable. When I find the slope, what I'm going to do, I'm going to step in the direction opposite slope, because remember, the slope is positive, this tangent is positive, and I want to climb down. I want to come down. So I'm going to take a step ahead in this direction. Right? So let's do that. My PPT is not advancing. I don't know why. Can you hear me, Vijay?
Yes. You can switch back. Yeah, you can switch back on the mode.
Can you see my PPT or not?
Yes.
Okay.
Yes, sir.
Fine. It's back to work, but apparently I cannot use my laser. Why? Okay, fine. Doesn't matter. So what we discussed here, we are going to do. I've written here. So compute the slope gradient, that is the first order derivative of the function at the current point, and we will move in the opposite direction of the slope. Because remember, slope is positive by default. And we want to climb down, so we will come down. So this is what we do. We calculate the derivative. This you see is partial derivative of the function, cost function, which is sensitive to weights of the neural network and the bias. We take the partial derivative with respect to weights that we want to tune, we want to change, right? We take a step ahead. How much of step? That is determined by a learning rate, which is alpha here. And we will come down, which means we will decrease the value of weights at that given instant. We will decrease it by this much amount. We will decrease it, remember, not increase it. And we update our weights. So our weights have decreased by this much of amount. Of course, how much we decrease at one given instant is determined by the alpha. So one has to choose alpha properly. We're going to discuss that very soon. So we are decreasing the weights in this fashion. And of course, we must do the same to bias also, because remember, bias is nothing but a weight when all your inputs are zero. So we must do that with bias also. So we do that with all the weights of the network. So we keep doing that at each point of time. And when we reach really down, then remember, when you are really at the minimum, the slope is going to be zero. So when your slope is going to be zero, this term here, derivative, is going to be zero. And when that is zero, well, you're not going to change your weights at all. So in fact, when you don't change your weights at all, it means that you have reached the minimum of the function, or you have in some way reached the saturation, right? So that's how we tune or we change the weights of neural network. Okay, I'm just going to see if there are some questions. Can we use, someone has asked, can we use genetic algorithm or differential evolution algorithm to tune the weights of neuron? Yeah, of course you can. And evolutionary genetic algorithms are used they have been used in the state of art by many researchers from different domains for tuning the weights. That's one way to do it. Of course, we are not talking about that, but learning, even there, is the philosophy of learning is similar. Well, evolutionary algorithms, they are very different from here. They are somehow related to the Monte Carlo based initializations, when weights are initialized randomly and then they are tuned based on different trials and errors. So we'll not talk about that here. Okay, so but there's a lot of literature out there. And okay, so we did that gradient descent. Let's go ahead. So what's going to happen now? We saw this earlier. The weights, they are updated using the total loss. Okay, we had six inputs. We calculated loss for each one of them. We added the loss. Okay, and now we are going to back propagate the loss into the network, and we are going to change our weights using this mechanism. So basically, this loss is going to be used. That's your loss function. This J is basically the loss function. Okay, this is going to help you to change the weights, and you will keep doing that till you reach the minimum, which means you have reached the minimum of your loss. Okay, let's do that. Let's go ahead. So let's summarize. We talked about this. So typically, if you look at the loss with respect to each epoch, usually you should have a loss which is usually the loss is very high, which means the difference between y and y hat is very large. But once you do this one time, well, it decreases. You do another time, update all the weights using total loss, which is batch update, full batch update. I would say full batch update. That is, it decreases. Full batch update, third epoch, decreases. Fourth, fifth batch update, eighth batch update, 10th full batch update. And by 16th, you see that your loss is not changing at all. So when your loss is not changing at all, it means the weights, they have reached their saturation, which means they have tuned themselves, which means that they have learned, they have reached the optimal values given the inputs and outputs. So the question is, what is alpha? Alpha is the learning rate. And what happens when learning is very slow and when a learning rate is very high? So usually what's happening here is, remember, you are climbing down. So if your alpha is very high, then what you're going to do is you're going to take a very high step, right? And you're going to oscillate between on the different walls of your cost function, which is not good. So basically, you may not reach the minimum at all, because you'll just be oscillating between different regions of your cost function. So it's not good to take a very high learning rate. And if you take a learning rate which is too low, well, you're going to have a very slow convergence. So you're going to take very slow steps ahead, and perhaps you will converge after many thousands of iterations, which is not good also. So it's a hyperparameter, like many other parameters we will talk about shortly. And it must be tuned. It shouldn't be very high. It shouldn't be very low. And we will see how it is done. But gradient descent, it works well when the loss function is a convex function. Well, that's usually not the case. Many a times you have functions which are non-convex. What to do? Well, when you have a non-convex function, then well, it's pretty tricky. It's pretty complicated. So what you're looking at is, let's say, this kind of terrain, this kind of mountain, which is not all beautiful, quadratic, but it has different small valleys and terrains. So what's happening? You're starting from here, this point. You're getting stuck at this point. You're not going to. What's going to happen? That you're going to get stuck in a local minima, and you're not going to find the global minima, and that's not good. So that's where, let's say let's say you have a ball which is here, and you want your ball to roll down to the global minima. So what you're going to do? You will want to jerk it a little bit, jitter it a little bit. This is known as jittering. This is in computers, in signal processing, we talk about noise, adding noise to the estimation, adding persistence, excitation of persistence. In the estimation theory, those who are from electronics would appreciate this fact that we need to add noise or persistence of excitation for the estimation to converge. And for those who are in computer science, you would know that we need to explore different regions. So this is known as exploration-exploitation problem, or trade-off, or routine. And the idea is to add some probability, add a stochasticity at each iteration step, so that each of a set of iteration steps, so that a certain probability is given for X to not get stuck in local minima, but to get out of it and find the global minima. So that's the point. That's the point. So what we are going to do, we instead of just being, instead of getting stuck in local minima, what we are going to do, we are going to add some stochasticity. We are going to jerk it a little bit. We are going to move it a little bit. We are going to add some exploration probability, which will help it to get unstuck if it is stuck in local minima, and eventually find the global minimum. So when that's the case, what we do is we are going to add a little stochasticity, and that is what is known as stochastic gradient descent, where what we do is instead of considering all the inputs at one time, what we are going to do is do this weight adaptation, back propagation, one at a time. So we will do it with first input, x1, x2, xm, first input, we'll do that. We'll calculate the loss. Okay, remember, now look here, this is not the total loss. This is just the loss with respect to input 1. So y hat, we have the real y, we calculate the loss. Loss here, you can see it's pretty large. Once the loss is calculated, it is propagated backwards. Okay, then second, second input data with x1 till xm, right? We get the y hat, we see the real value, we take the difference, we calculate the loss, loss is little less, and we propagate backwards and change all the weights. Okay, then third, we change the weights, and remember now what's happening, we are changing the weights, but these data can be different from each other, and if the data they are different from each other, it means basically the data is belonging to different state space, and it means that we are exploring different state space. So we are adding stochasticity, we are adding a certain probability that indeed the y, the input, the difference, the error at input 3 might be very large compared to the error at input 2, which means if the error is very large, what's happening here? Well, you might have a small error here, but up here, the next step, it will have a large error, and this large error will give it some probability to explore and finally find the global minima, right? So that's the whole idea. So that's why we do, that's what we do here. We do it the same with input 3, where we can have input 4. Well, here the loss is going down, but we can have a large loss also, which is what stochasticity is. Okay. Then finally, we do this with both the data, the 5th data and 6th data, and each time we do it, propagate back the loss, we propagate back the loss, propagate back the loss, propagate back the loss, propagate back the loss, and change the weights, propagate back the loss and change the weights. And finally, when we have done this with all the data, then we say we have done one epoch of training. One epoch of training has been done. Okay, so we iterate the whole thing until convergence is detected. Okay, until we see no more change in the weights, we keep doing this. And this is what is known as stochastic gradient descent. So in fact, in the loss in stochastic gradient descent will look something like this. It will function, it goes down globally, but you will see that locally it comes up and then goes down. So it's a kind of oscillating function, but globally it goes down, ideally. So, right. So we are updating weights after each training data sample. Right? We talked about all this. So let's look at the difference. What's the difference between batch gradient descent and stochastic gradient descent? Well, the batch gradient descent, in the batch gradient descent, there's a noise from some participant. Please mute your micro. I would say that would be Madam Dipti. So the batch gradient descent has here all they are processed at one time, and the stochastic gradient descent here, each input, the weights are updated with respect to each input data. please switch off the microphone.
उसमें just suggestion है उसमें
Please.
मतलब ये final है okay?
Yeah. So that's your stochastic gradient descent. That's the difference between batch gradient descent and stochastic gradient descent. But remember, in stochastic gradient descent, the updates are happening after each data sample. So, well, although it seems it's going to be a large, it can consume a lot of time, but in fact, it is less time consuming because of the other time complexity factors, which we'll not go into right now. So the neural networks, they are updated after each data. The memory is not allocated to all data at once, which explains why stochastic gradient descent is pretty faster than batch gradient descent. But it cannot really vectorize the computations. So, you cannot really make all the computations very fast with stochastic gradient descent. What's going to happen? You have millions of data, a lot of data, and you have limited memory. What's going to happen? Well, it's going to take a lot of time. So there has to be a trade-off. So here researchers, they ask themselves, can we mix the full batch update and stochastic gradient descent based update? Can we mix them in some way or the other to have an efficient trade-off? So that's where the concept of mini batch gradient descent comes into play. So you have mini batch of gradient descent, which mixes the advantages of both gradient descent as well as stochastic gradient descent. So here you are not typically processing one whole batch, all the input data sets. What you are doing is that you are going to select a mini batch. So here this mini batch can be composed of 2 input data, input 1 and input 2. So that's your first mini batch. Your second mini batch can be 3 and 6. And your fourth mini batch can be, well, first and third, like this. You mix and, you can create your batch in several ways. And for each batch, you pick your mini batch, okay, and you feed it to the neural network. You calculate the mean gradient of the mini batch, okay. So basically, the gradient with respect to this data and this data, because remember, it's with respect to the whole batch, the mini batch. Calculate the mean gradient that we talked about, and repeat the same steps 1 to 4 for all the mini batches. So basically, you take into account this mini batch, you take into account this mini batch, then this particular mini batch, and you permute and you go through all the data at least once. When you have gone through all the data at least once, you say that you have completed one epoch of learning. So that's your one epoch of learning right there. Okay. So is that okay? Do we have some questions? I see the chat box. I see no questions. That's good. That means either people are sleeping or they are understanding. I hope the former is not true. So, great. Now we know how the neural networks, they update their weights. So basically, now we know how neural networks are learning using batch gradient descent, stochastic gradient descent, or mini batch. But question is, how to calculate? Now, you saw these 2 equations. That's pretty good. But the question is, how to calculate this cost function? This cost function को कैसे calculate किया जाए? That's the whole question. What to do about it? That's what we are going to learn in backpropagation, how this gradient is calculated and how this gradient is used to update the weights. So that will be the subject of backpropagation that we will discuss tomorrow, I guess, because I think the time here, I'm running short on time. It's 3:30 in India, 3:32 in fact. Vijay, would we have some time today? Shall I continue for some more time, or How would you like me to take it?
It's your wish. If suppose you want to continue for a few minutes more, you can continue.
Okay, so let's continue for 15-20 minutes.
Yeah.
Is
Okay.
that right? Okay, perfect. So let's continue for 15-20 minutes and let's complete the back propagation. Right. Let's see. Okay. So let's go ahead. Back propagation. What is it? Well, it's the algorithm which helped us to accelerate the research in neural networks. Thanks to Geoffrey, the student, and it was proposed, I think, in 1986. And since then, there has been a lot of research, a lot of variants. And so, what is it? Well, it was not proposed in 1986. In fact, it was rediscovered in 1986 as a very efficient way of propagating backwards the error gradient and updating the weights. Okay. Let's first look at what is forward propagation. So this forward propagation is easy to understand. Input data goes through a set of neural nodes, neurons, goes through the summation, goes through the non-linearity. So you have the non-linear function here. Then you have the output, which goes through another layer, the second layer with their weights. And then you have the non-linearity and summation. And then finally, you have the output of from the network. That's your forward propagation. Go to the loss. You go to the loss, calculate the loss with respect to the actual data, the actual output, and that's the forward propagation. So several people are asking if I would share these PPTs. I would share these PPTs in some time. I'll send the coordinator, and perhaps the coordinator can send you all. Yeah. So don't worry, you will have the PPTs, and just when you use these PPTs, please do not forget to cite me. And yeah, that's your forward propagation, and that's your. Let's look at the propagation again. So that's your first layer. Input data is coming, multiplied with the weight sets, goes through the summation and non-linearity. So that's your second input to the second layer. The second layer has its own set of weights. Okay, goes ahead, and you have y hat. And you have the loss function, which is the square function, and taking into account the difference between y and y hat, the loss is produced. So that's your forward chain. That's your forward propagation. Of course, here I have made some simple assumptions. Here I'm not taking into account the non-linearity. It's just a simple multiplication because, well, because for the sake of analysis, that's all. So that's your forward propagation. Remember, what is Z? What is Z? Z is W multiplied with X. Then Z becomes the input to H. Then H becomes the input to the second layer multiplied with H. That leads to Y hat. Then you have loss here. Now, that's your forward propagation. Now, let's talk about back propagation. There is a question here, Madam Meenakshi Pathak, the implementation tool. So I will be talking about implementation tool in the last lecture. I hope I still have time to show you how it can be coded in Python. But if I don't have, then in any case, rest assured that I will be talking about different options available Python based mostly, like TensorFlow or PyTorch. Yes, if you have Anaconda, please install them. That would be useful, and you can go through some Jupyter notebooks. And Python is very easy to learn. And all this forward propagation and back propagation can be very easily done in a single line of code. What's essential is to understand how it happens, which is what on which we are spending some time here. So forward propagation you understood. Let's talk about back propagation. So in back propagation, what's happening is we are I'm sorry, I cannot. Yeah, okay. Okay, so let me remind you of the chain rule in calculus, the basic calculus. The output y equals function of x. So, and let's say you have a composition of composite functions, function of function, and that is, let's say, z equals gy, where y is function of course, f. So basically you have gof of x, okay? In that case, if you take the derivative of z with respect to x, what you get is basically the matricial. If that's a matrix, you are getting a matricial product, a matrix product of partial derivative of z with respect to y, multiplied by partial derivative of y with respect to s, and that's how you calculate the partial derivative of z with respect to s. Right? That's how that's the basic chain rule of calculus, and that's all it is used. That's all. Using on the basic chain rule, you can calculate the derivatives. Now remember, to do the learning, remember.